So this is going to be for Unit 7, Worksheet 3, Circular Motion Examples. The second problem has an scenario of 6 children running on a track with equal speeds. Their masses are expressed in multiples of mass with a capital M, and their path radii are expressed in multiples of radius with a capital R. Part A, we're trying to rank the centripetal acceleration of the lettered children from largest to smallest, noting that ties can be possible. And then the second part of this problem, part B, is ranking the centripetal force needed for each child to remain in circular motion. Once again, ties are possible. Now I'm going to show how we can do this determination for just runner A. And then it'll be up to you to figure out B through F for the runners, and then rank them accordingly. So for part A, we're trying to figure out what the centripetal acceleration can be. Now our centripetal acceleration is A for acceleration and a subscript of C for centripetal. The centripetal acceleration in circular motion is the square of their speed, or the average velocity, divided by their radius. Now if we're doing this for runner A, well, we're not told what their speed is, just that it's going to be the same as every other runner. So I can keep that v squared just as it is. Then I just need to look to see what the radius is actually going to be for runner A. So this is runner A right here, and they are part of this curve. So it looks like they have a radius of 4r. So for runner A, they really have 1/4 of our v squared divided by the radius. Now we can do the same thing with all of the other runners to see which of those has the biggest or the smallest prefix here, because all of them still should have that same speed, the v squared, as well as the same r for radius. The only difference is how many r's that would be, which comes into this prefix. So we just need to really compare the prefixes here to determine which has the largest centripetal acceleration and which has the smallest. Now for part B, where we are ranking the centripetal force needed for each child to remain in circular motion, we just need to use our equation for centripetal force, which is the same thing as our net force, which is our mass times our centripetal acceleration. Well, we know from above our centripetal acceleration is the square of our speed divided by our radius, and we still have our mass. So we just need to take the mass and the radius for each of our runners. So once again, I'm going to go with runner A. Runner A has this mass of 4m. 4m times the v squared, because their speed is constant, so it's staying as a v, divided by their radius of 4r. Now, in this case, I'm just going to rearrange this and give me my prefix. It's 4 divided by 4 times our m times v squared divided by r. Now this second term here should be the same for every single runner. What is going to be different is the prefix. This right here can also be simplified down to just 1/1 if we're rearranging our fraction. And we're just going to be comparing that prefix there when we are setting up our ranking of the centripetal force.